In this video, we're going to talk about the line integral of a vector field. And when we previously talked about line integrals, we would have some path, and then we had some function that gave us sort of height above every point along that curve. But now we're imagining a scenario like this, where we've got some vector field, and we've got a curve that is moving through the vector field. And if you look at this vector field, sometimes the arrows of the vector field appear to be almost tangent to the curve. Sometimes they're pointing completely away from the curve in all sorts of directions. What we want to try and measure here is some way of capturing the degree to which the vector field goes along with the path of the curve, and the tangents of the curve and the vector field are aligned. So what does that mean? Well, let's start with a more concrete example from physics, the concept of work. Indeed, you might recall that work was defined to be a force times a distance, a sort of an elementary way of thinking about what the concept of work is. If you apply a lot of force for a long distance, you've done a lot of work. The standard example of this was an inclined plane. We have a block. The plane is assumed to be frictionless, and the block is going to be sliding down the plane under the force of gravity. It might move, well, a little bit like this. So if we analyze what's going on here, there's a force of gravity on that block that points straight down. But you can decompose that force of gravity into two different directions. A proportion that is normal to the inclined plane and a portion which is tangential to the inclined plane. Indeed, I'm also going to add a vector which I'll call t, and this is just showing what is the direction of that inclined plane. So because the block moved along that inclined plane, the proportion of the force of gravity that was normal is irrelevant. There's no work that's being done in that direction. All of the work that was done was the proportion that was moving in the tangential direction. So how much work is actually being done? Well, if we say that there is a distance d between where the block started and where the block ended up, then what we can talk about is the dot product, the proportion of the force of gravity in that tangential direction. That's the force that we're interested in. It's not the entire force of gravity, just the proportion of the force in the tangential direction. And that's what a dot product captures. And then you multiply that by the distance d. Okay, so pay attention to the fact that our work here was defined to be a force dotted with the tangential. And let's zoom back out to our more complicated situation where I have some field, and then I have a curve that is going to be going through that field. And then the question is, what is the work done by that field if I move some particle along that curve? And as we just saw, the answer to how much work done is going to depend on the degree to which this curve is going tangential to the field. So let me zoom in on a little portion of the curve and analyze what's going on here. So if I take some spot and I'm going to measure a little unit of ds, I'm going to imagine that I'm just moving some small amount along the curve, a little change in arc length, we call it ds. And then I'm going to say, well, in that small little region, I'm going to have some vector field, and it's going to point in some direction. So I'll put that vector for the f. And then if I'm interested in what is the work done by this little movement of length ds, I also have to ask, well, what is the tangential component? So then the contribution of the field along that little segment ds is just given by the f dot t, that's the proportion of the force in the t direction, times this little ds. If I'm interpreting this as work, then I would say the work done from moving that little ds is this f dot t ds. Finally, I had a much bigger curve, and so if I want to add everything up, I'm just going to integrate it. I shall do the line integral of a vector field f along the curve c is just given by this integral over c, the same line integral we've seen before. It's just that the integrand is the f dot t, and then integrated with respect to ds. So this formula is exactly like the line integral formula we've seen before. Indeed, it's defined in the exact same way. It's just the integrand is different. The integrand is not just an arbitrary function, which is what we've seen before. The integrand is the specific thing. It's trying to capture the influence of the field along the curve, and so the integrand is this f dot t. And so putting the picture back up, we have an answer to the work done if you move the particle along this curve in this particular field. And indeed, I've been talking about work so far in this video, that specific physics concept, but indeed the concept of a line integral of a vector field along some curve is something that applies in many different scenarios. Work is just one of them. So this definition applies broadly. This is a definition we can understand because we previously understood the concept of a line integral. But the question now is, how do we compute it? And as we've seen before, when it comes to computations, we want to see how can I parameterize a curve explicitly and then rewrite this formula in terms of that parameterization. Okay, so let's give some labels. I'm going to say I have a parameterized curve. The curve is on some interval of t between a and b. And then the curve is going to be a g of t in the I hat, an h of t in the j hat, and a k of t in the k hat. The way I think about this is the vector r is a vector that goes from the origin out to the curve. So if the origin is in the center of this plot, then the r of a, so that's sort of the first component on my interval of t from a up to b, points to the start of the curve. And then the r of b points to the end of the curve. Note, by the way, the curve has a little blue arrow here that indicates the direction that it's moving. Indeed, this is going to be very important. When we think about curves, we always want to think about them as starting at one spot and going to another spot. These are sort of directed curves. They have a direction that you're traveling. And that's implied by this choice of parameterization as well. Okay, so that's the parameterization for the curve. So now I want to go back to the formula I had. There are several changes I can make. Notice how there's the unit tangent vector t in this formula? Well, a definition of the unit tangent vector t was just that it was the derivative dr ds. So if you have a specific parameterization, you can say, well, how much does that position vector change as you increase arc length? That was the definition of the unit tangent vector. And then just by the chain rule, ds, I could replace that with ds dt dt. So again, with chain rule, the ds's cancel. I mean, they don't cancel exactly, but that's the result of the chain rule. And as a result, I can plug this in, and what I get is the field, just evaluated now along the curve, so f of r of t. And then I multiply it by the derivative dr dt. That's a dot product between this field and this derivative. And then I'll integrate it out with respect to t, and my limits of integration are in t as well. They go from the a up to the b. So while the left side of this equation is the definition, the right side of this equation tells me how I compute it. It gives me an explicit way to compute this. And indeed, we're going to run through a concrete example computing a vector field along a curve in the next video. But before we end, I want to show you just one more piece of terminology. It's a third way to think about this. If we have this dr dt dt, I can just define a new symbol, which is just dr, just to be a shorthand for that. And so my third way of writing this is the integral along the curve of f dot dr. And all of these things are the same, it's just different terminology. So sometimes you'll see a line integral written f dot dr, sometimes you'll see it written f dot t ds. Whenever you want to compute it though, whenever you actually have an explicit parameterization, use the middle one, this f dot dr dt dt. The middle one is how you compute it. Anyways, we just want to be a little bit familiar with being able to alternate between writing things ds or dr or dt. They all refer to the same thing, just some might be more natural in one context than another. Alright, if you enjoyed this video, please give it a like for the YouTube algorithm. If you have a question about the video, leave it down in the comments below, and we'll do some more math in the next video.